Hi, hello. Welcome to this video. My name is Wong. I'm from University College London. Today, I'm going to talk about fluid antenna system, a new form of reconfigurable antenna technologies for wireless communications. So in the following time, I'm going to give you an overview of what fluid antenna system is, why we need it, and some potential applications for 6G wireless. The purpose of today's talk is not to cover the mathematical background, system models, signal processing, optimization, etc., etc. It's not about all these technical details for antenna system. But the main purpose of today's talk is to help the community identify new research directions that they could easily find for antenna system be useful into their own research. Okay, so here's the outline of my talk today. So first of all, we talk a little bit about motivation because we have 6G targets to meet. And what do these targets mean in terms of the technical challenges? And then I'm going to talk about what is fluid antenna system, why we need it, what it is. And the main focus will be on the potential applications that we will spend some time on it, okay? So before the end of the presentation, I'm going to talk about some latest experimental results for the prototypes of fluid antenna systems, and finally conclude my talk. And of course, over there, you see Bruce Lee on the right. Okay, so why Bruce Lee is here? How is he relevant to my presentations? So I'm going to explain that later on, okay? So 6G, okay, so everybody working on wireless communications would be motivated by 6G, okay, the development of 6G basically. So over there, you see a lot of these sort of KPI, key performance indicators for 6G. We have, the data rate requirement, latency requirement, positioning requirement, etc., etc. There are a lot of these, okay? So we have been very familiar with these, okay? But I particularly like the interpretation by Professor Yeo from Southeast University. They published an article last year in the IEEE Wireless Communication magazine. So it's about 6G, okay? What is 6G? So in their interpretation, 6G is what they call TK-mu extreme connectivity. So T corresponds to terabit per second scale data rate. So this is actually the first major target, the data rate target that we need to hit terabit per second. The second one is about kilobit per second per hertz scale spectrum efficiency. So basically for each use of spectrum, 1 hertz of spectrum, and we need to hit 1,000 bit per second. Okay, and also we have the requirement of latency, which needs to be very, very small in a microsecond scale. Okay, so this is quite easy to understand. Okay, so in terms of challenges, for the first one, actually is very, very difficult. But from my expertise, because I'm not a device people, I don't, design. I don't have expertise or knowledge to know how do we design energy efficient or low cost terahertz devices. So I would say if you're giving me a terahertz band, okay, so I should be able to hit a terabit per second easily, okay, from the physical layer, from the codec design, it's pretty straightforward, okay, if you give me the terahertz band, okay, of course, given the fact that, you are in the coverage. But okay, so the main challenge is not on the physical layer or the communication theory side, but I think the challenge really would be on the device level. How do we make these device energy efficient and low cost? Okay, so the second and third items, okay, the target is probably more, definitely more relevant to my research. My own research is on the physical layer and a little bit of up, okay, but mostly physical layer. So if then we look at the second criteria, that would be really killing us, okay? Per hertz, kilobit per second. What does that mean? So if we are to, okay, hit 1,000 bit per second, if you're giving me 1 hertz, so what does that mean? These either means that, okay, so we are using the classical shunt capacity formula, and then log to 1 plus signal noise ratio. Let's equate this to 1,000, the target that we want to hit. that easily would translate into signal to noise ratio level of 3000 dB. That's of course ridiculously high, okay? Or if we consider some kind of like spectrum sharing scenario where 1 hertz of bandwidth is being shared by U users, okay? So then in that case, we could say, okay, so we need U times log2 1 plus signal to interference noise ratio. Now we have interference in play because we allow these spectrums to be shared by U users, okay? And assuming that, all of these users have, similar or identical performance, then we need these numbers to be equal to 1000. Then in order to get these 1000 values, okay, what that means is maybe we allow 1000 users to share the same spectrum, same 1 hertz of spectrum, and each of these achieve signal to interference noise ratio about 0 dB, okay, then you can actually hit 1000 as well. So I think the right way of interpreting these target will be on the right-hand side, okay, because the left-hand side, basically, you would need a power plant to power your signal, which doesn't make any sense at all. So therefore, the target of 1000 bit per second per hertz of spectral efficiency for 6G basically require extreme multiplexing, okay? So we need the spectrum to be shared by a huge number of users, to hit that target, okay? But at the same time, we need to understand that if we are to allow huge number of users to share the spectrum, then we need to do a lot of management, particularly interference management. So in the current technology state of the art, we need to do a lot of maybe power control, interference management, maybe pre-coding, et cetera, et cetera. So that could be a problem. So remember, another target that we need to hit for 6G is microsecond latency. So the bottleneck, okay, for very small latency, to me, in my opinion, is about the protocol. We need to make the protocol a lot lighter, a lot simpler, okay? But a simpler protocol isn't really what we're heading, okay, towards for 6G, okay? Because, from the experience that we had from 4G to 5G, we're actually getting the protocol increasingly bulky, more complicated because of the increasing requirement of getting more channel state information, getting more network information so that we can do more intelligent signal processing, in particular, for example, pre-coding, right? We need to get channel state information, get feedback, etc. There's a lot of overhead involved that make the protocol so much more complicated. So therefore, if we need to consider extreme multiplexing and latency requirements together in somehow, then we should expect that no matter how we're going to achieve this extreme multiplexing, we should try to stay simple. Well, now it's time to evaluate what are the existing technology or the emerging technologies and whether they are hopeful to sort of meet these sort of targets in the future. So obviously, okay, the most talk about technologies are this, okay, massive multi-source MIMO, NOMA, RSMA, cell-free, AI, etc. Okay, so I'm going to talk a little bit about massive MIMO, later on in a minute. But NOMA, RSMA are sort of new multiple access technologies that are increasingly interesting, okay? There are a lot of attentions in the past few years, okay? Because of the fact that these two technologies are so powerful, you can allow users to overlap on each other, okay? And then you do some kind of power control, or if you select appropriately what users to be overlapped, and then, okay, do interference cancellation in the users, then you would be able to turn these sort of hostile interference limited channels into a high capacity channel. So these are really, really powerful technologies, okay? But do we expect NOMA or FSMA to be applicable to multiplexing of a huge number of users, 5 users, 10 users, or maybe more, 20 users? Well, this is inconceivable, okay? So therefore, no matter how powerful, how attractive NOMA and RSMA, I probably don't believe that these would be the technology that would be able to take us to spectrum sharing of huge number of users, let's say 10, 20, 30, 100 users. No way, right? There's also these sort of increasing interest for cell-free MIMO. Okay, cell-free MIMO basically we just allow these base station different servers to share their antennas to do this sort of coordinated joint signal processing. Okay, which is, by the way, really beautiful idea. Okay, but in practice, of course, it's not so easy. Okay, because of the increasing requirement of channel state information and optimization, so on and so forth. Okay. How about AI? Okay, so AI is definitely the future. Okay, not just for physical layer, but for upper layers as well. When it comes to the optimization of the whole wireless communication networks. Well, but we need to understand that no matter how important or how powerful AI is, AI at this stage, at least we don't expect AI to be able to invent new physical layer technology. Okay, so AI is not going to invent new communications technology, but AI more or less would be a tool that allows us to give them options, and then AI would be able to return to you the best possible solution. Okay, based on those options. Okay, so it's more like a stronger, more powerful optimization tools. Okay, so to speak. So what about massive multi-user MIMO? So when we talk about massive multi-user MIMO, we need to understand that, okay, MIMO actually began from 1994 due to a patent filed by Professor Paraj, okay, and Thomas Kalek, okay, from Stanford University, but in 1994. But people didn't pick it up. Okay, didn't realize the power or the potential of that patent until 1998. A group of people's the work led by Dr. Fasuni, okay, from Nokia Bell Labs. At the time, it's AT&T Bell Labs. The paper, okay, they publish about how do you actually utilize, okay, MIMO to increase the capacity of a point-to-point link. So these results actually change everything. Okay, since then, actually, MIMO has been impacting third generation, fourth generation, and now 5th generation. And then we expect this to, we see MIMO 6th generation, 7th generation, and so on. Okay, because it recognized the fact that MIMO actually brings with us new degree of freedom that we can manipulate and we can process that to deliver so much gains. So since MIMO back from 1994, MIMO has taken a few evolutions. Okay, one major evolution is the multi-user MIMO, which began from year 2000. Again, people didn't notice much about multi-user MIMO, even though it was published back in year 2000, until a few years later, 2004. There are some classical papers that people love the results about multi-user MIMO back then. So since then, actually, multi-user MIMO become a crucial part of wireless communication. It's now being used in Wi-Fi 5, 6, 7, 4G, 5G, right? So therefore, it actually becomes the core technology. So how about 5G? What do we have? So in 5G, we have what we call massive multi-user MIMO. It's still multi-user MIMO, but massive. Maybe because of the fact that we're actually having 64 base station antennas, and then to serve up to, let's say, 12 users, okay? Let's say in the downlink. So we see an excessive use of the number of antennas at the base station. So therefore, it's kind of like massive, right? Massive MIMO, right? Well, but if you look at the protocol, okay, for 5G, in fact, they are not actually doing match filtering, okay, precoding. They're actually doing COBO-based precoding, and which is based on maximizing the signal to incident noise ratio. So my understanding is that the COBO-based precoding for 5G is actually trying to achieve MMSE precoding instead of match filtering precoding. Okay, so therefore, this makes us wonder why, when we have 64 antennas in the base station, and then if we are not using match filtering, and we're using MSE precoding or serial forcing kind of precoding then we don't have to just serve 12 users, right? Okay, because we're doing we're doing the maximization of signal to interference noise ratio. We have 64 antennas at the base station, 64 RF chains. We can, in theory, serve up to 64 users in the downlink. Why we stop at 12? So that's made me wonder, where is the bottleneck? Okay, the bottleneck is definitely not the number of base station antennas, because we do have enough RF chains to do the signal processing. And we are not doing much filtering, so therefore we don't need the excessive number of base station antennas over the number of users. So it turns out that the bottleneck is the CSI, the channel state information at the base station. So the current 5G actually says that, okay, we can only do up to 12 users. More users involve too much overhead, or we may not be able to estimate the CSI and then get them feedback to the base stations soon enough, okay? We cannot make sure that the CSI's quality is good enough for doing the pre-coding. So it's not worth, okay, scaling up for serving more users. And that's what's happening. So therefore, with this understanding, and then also recalling that what we want is to serve much more users, okay? So let's say not 12 user, but let's say 120 user, 240 user, or maybe 500 user, 1,000 users, right? Remember, 1,000 user, okay, let's say 0 dB signal to interference noise ratio, right? So then obviously it's difficult to see how multi-zone MIMO would cope, okay, in the next generation if we are to increase the number of users to be served on the same channel massively, okay? So we need something different, okay, to assist it, okay? If we have some other approach that can replace multi-zone MIMO, why not? But of course, I don't think this would be the case, but we should be looking at completely different approach that hopefully would be able to complement multi-zone MIMO to do things better, so that we can, have a much more desirable scalability. Okay, so that is the situation for 6G. And remember, don't forget that we need the processing to be as simple as possible, because we would want to keep the protocol simple, for latency purpose. Right. So we need something else, in order to look for something else, in my case, I took inspiration from Bruce Lee. So who is Bruce Lee? Okay, Bruce Lee is a martial artist and a movie star. He was so active in movies, okay, in the United States or in the Asia, as well in the late 60s, early 70s, before he passed away. So he doesn't just love martial arts, he's obsessed with martial arts. He practices judo, Wing Chun, okay, karate, taekwondo, wrestling, and many others, okay? So he was just so obsessed, he tried to understand the pros and cons of different martial art systems. And eventually what he tried to do is to come up with his own ideas about combat, okay? And in his version, he developed the new martial art systems called Jeet Kune Do, okay, Jeet Kune Do, okay? And also, he felt like sharing the idea of Jeet Kune Do in one of the episodes of the show called Long Street, which was aired in September 1971, right? This Long Street, okay, a TV series. So in one of those episodes, he shared the idea of Jeet Kune Do, and that's what he had to say, okay? He said, empty your mind, be formless, shapeless like water. If you put water into a cup, it becomes the cup. You put water into a bottle, it becomes the bottle. You put it in a teapot, it becomes the teapot. Now, water can flow or it can crash. Be water, my friend. Well, to me, okay, a good summary of his philosophy is basically the last sentence. Be water, my friend. Okay, that actually resonated me a lot. Okay, I resonate a lot from reading this philosophy, because I draw a lot of parallels and similarities between what happens in wireless communications research. In particular, I think due to the hostility of wireless communication channels, and then we have path loss, shallow feeding, multi-path feeding, huge interference, and we also have other constraints like complexity, energy consumption, etc., not to mention, these other emerging applications like computing, security, sensing, the list go on and on. Then the hostility of wireless communication channels makes it so difficult to deliver the reliability, okay, for communication, okay. So what happens over the past few decades, and then we see channel coding, power control, resource allocation, adaptive signal processing, equalization, a long list of techniques that people came up with, okay. All these researchers, professors, work their socks off to come up with all these ideas. So my understanding to this is, well, then there's a lot of similarity between what Bruce Lee faces in combat, okay, and what engineers for wireless communication face, okay, in reality, okay, because the hostility of wireless communication channel, and then we end up doing a lot of flexible designs, adaptation, right, optimization. All of this is like be water, my friend, is exactly what Bruce Lee was proposing, okay? But he was proposing these for combat, but the engineers were proposing these to combat wireless communication channels, right? So Bruce Lee, in his philosophy, he said, be water, my friend. So then at one point, then I resonate and I say, be water, my antenna. That create a new concept I call fluid antenna system, okay? So basically just to capture that sort of spirit of being flexible, being completely flexible, okay? So in particular, these concept fluid antenna system, abbreviation FAS, okay, represents shape flexible, position flexible antenna systems, okay? And that's the concept. It is not specific to any implementation approach. This concept doesn't tell us, how do we implement these ideas? And in fact, later in this presentation, I'm going to go through a number of emerging technologies that people try to sort of recreate these ideas in practice. Okay, I'm going to go through those. Okay, but FAS for internet system is a concept. That concept captures the shape, flexibility, and position flexibility of antenna. Okay, so we published a few papers on that, and as early as 2020, and then we already had this concept, and then we start working on this ever since. So the easiest way to understand this concept is free antenna system actually offers a new degree of freedom in physical life. This is important. If you have a fixed antenna, just like a conventional communication system, what you get is a single signal in space. But if you have free antenna system, okay, then in fact, instead of having a single point in space, a signal at a single point in space, you could have a signal spectrum in space, okay, with high resolution, okay, with high resolution. Then these, of course, expand the degree of freedom. It generates a lot of possibility for new coding technique, new signal processing, new optimization, and so on, so forth, okay? It's a new degree of freedom. But of course, more than that, it of course innovates other ideas like, I'll talk about later on, like, how does that innovate multiple access technology and so on. But the easiest way to understand this is a new degree of freedom. Well, free antenna system, like I said, is a concept, okay? So with this concept, of course, people can do a lot of research like me, I have been doing this over the past few years. But of course, I need to also try to answer one question, because during the past few years, a lot of people came to me and say, okay, this is a great idea, but is it real? Okay, is it just a concept that nobody know whether this will be realized in practice for the next 10 years or so, right? Okay, people have different priority. Okay, if this is not real, probably they would be more interested in some other ideas, okay, to explore other areas, okay? So therefore, since maybe 2-3 years ago, and then we start exploring ideas to implement this, okay, for real, okay? So today I'm going to just quickly share 3 possible ideas, and then of course there are other ideas are possible, okay? But today I'm going to just limit to 3 ideas that we ourselves try, okay, for the past few years, okay? The first ideas was liquid-based, okay, free antenna system. This one was led by my colleague, okay, Professor Kenneth Tong from UCL, in collaboration with Professor Wong, okay, Steve Wong from City University of Hong Kong. That is the picture of the prototype that we actually made 2 years ago, 2-3 years ago. So you can see this is antenna. There's like a container inside. There's a liquid metal that we are able to shift in one sort of dimension. So we actually using electronic pump that we can pump in and out to actually shift the liquid metals to change the position of the radiating element, and then we succeed on that. And then in fact, these antenna is so good in taking many boxes for antenna, okay, and also we have these position flexibility as well. And if you're interested, you know, you can download this paper from archive.org that we upload. Excuse me. But increasingly, I realized there's one limitation for this idea, which is the speed of changing the position of the antenna. Okay, we can push it to like 1 second or half second, okay, to change the position by, let's say, 10 centimeter. Let's just say, for example, in 1 second or half a second or less than half a second, okay, we can actually do it. But is this good enough? Well, this is complicated. I think you could find application where this will still be useful. But to me, my interest is always has been on thinking about how do we manipulate, okay, or exploiting the physical layer, okay, of the signal. So then I always want to respond to channel fading, like the slow fading, right? So that means that I would want to have the position change of the antenna in millisecond, okay? Why millisecond? Because this is the typical coherence time of channel, okay, 1 millisecond. So if we want to change the position by several centimeter, okay, distance in millisecond, that would never be possible if we're using a movable sort of mechanisms to achieve the position flexibility. There's no way we can achieve this, because this would end up a design as dangerous as a gun or, you know, or rocket. Okay, so that would really be, you know, impossible. So therefore, later on, you know, in recent times, so we turn our attentions to 2 other design. One design is the so-called pixel reconfigurable antenna system. So this work is led by Professor Ross March from Hong Kong University of Science and Technology. The details of these designs, okay, you can find it from this paper on the archive.org, which we just uploaded 3 months ago. So this is one of the prototypes that he created, okay, his team created. So if you look at this, you may feel like, okay, that looks like a RIS, right? Reconfigurable intelligent surfaces. But I have to tell you that, no, it's totally different for the following reasons. Because if this is a RIS, okay, technology, you would expect each of these would be a unit cell. And each unit cell would be like a radiating element. So it's like an antenna basically, right? So, antenna picking up signal and then bouncing the signal back. So that will be what we would have expected if this is an RIS, okay? But this is not, okay? In fact, each of these cells is just some inner structure of an antenna. So these all is like a piece of a puzzle, okay? And the connection between all these little pieces, okay, needs to be optimized, okay? By some kind of optimization, we would be able to optimize those connections between these elements so that after optimization, it would become a working antenna with certain shape, certain polarization, and certain position. So therefore, let's say these one probably end up getting like 12 reconfigurable states. Each state could represent an antenna operating with certain shape, form, position, okay? So this is, what we have made, and that actually achieve the functionality of free antenna system concept. Okay, another idea is what we call meta design. Okay, using meta materials design. Okay, this work is led by Dr. Boyang Liu. Okay, not from Sustat now, from Shenzhen Technology University, in collaboration with Professor Steve Wong from City University of Hong Kong, and my colleague Ken Tong from UCL. So this is what they make. So basically, an antenna with some kind of metamaterial structures on the surface where they can electronically control so that the aperture of the antenna can be relocated. So we can then relocate the aperture of the antenna anywhere we want on the surface, which is basically a position flexibility. Okay, so this free antenna system is not just a concept; it's as real as you can get. Okay, and in the near future, definitely we're going to see some improved versions of these as well. So before the end of today's talk, I'm also going to share some latest experiment results using these two prototypes. Okay, so right, like I said at the beginning, today's talk, the purpose is not to cover the theory, okay, the analysis, the mathematicals, okay, models, okay, the signal processing routines, estimation techniques. We're not going to cover all this ideas, okay, not the details of a free antenna system, because that could be a lot, okay. And in fact, we spent a year, okay, 1 year, okay, exactly 1 year with so many people try to write about free antenna system, and then we finished a tutorial paper on free antenna system for 6G, and we uploaded on archive.org, and then you can go download and then read this paper, like 50 pages long. It covers almost every aspect of free antenna system, and with a very good and up-to-date list of references on this topic. So if I am to do a presentation on that, it would take a couple of hours. Okay, so no, it's not the purpose of this video. Okay, so the purpose of this video is all about potential applications. Okay, how free antenna system could be useful for 6G or future generation wireless continuous systems. Okay. Potential application. There are quite a lot, okay, and I have selected a few easy to understand and scenarios which we can utilize for antenna system for good purpose, okay. But in short, in general, in fact, free antenna system could be placed at user, could be placed at sort of on the wrist, it could be placed at the base station, could be placed at the UAV or vehicles. In fact, anywhere, okay, you can just upgrade your antenna system in whatever devices that you have, and then make it completely adaptive in terms of the shape and position. And then you have this, and then you increase the degree of freedom, and then you can do all sorts of things that you want. security, sensing, communication, computing, all sort of thing. Okay, so the first potential application I find it very useful is this. We call it MIMO+FAS. Okay, this resource reported in this paper. In this paper, we consider a single user MIMO link. Okay, so we have a MIMO. Okay, multiple antenna transmitter side, multiple antenna receiver side. But the difference here is that we allow the position of the antenna to change. Okay, to be able to be optimized. Okay. And then with that, okay, then we can look into the diversity order, okay, between, okay, the fixed position MIMO and then the flexible MIMO, or, you know, the MIMO+FAS setup, okay, to see what gain that we have, okay, when we introduce position flexibility into the MIMO system. Well, diversity order. What is diversity order? Diversity order is the measure in which, you know, how fast the error probability drops, okay, as the signal to noise ratio increases. So therefore, if this number is large, that means that the error probability drop much quicker. Okay, so this is what diversity order is used in analysis. So one example, if we have a half lambda and a half lambda space, okay, half lambda space at the transmitter side, receiver side, then in fact, we can show that for fixed position MIMO, at most you can get 16. That is the diversity order. But once we allow the position of the antenna to change position, the diversity order jump, okay, given the same space, okay, jump from 16 to 169. 10 times, so basically more than 10 times increase in the diversity order. Of course, if we increase the size of the antenna surface, let's say from half lambda by half lambda to 1 lambda by 1 lambda, you increase the diversity order for fixed position MIMO, but then the MIMO+FAS diversity order also increases. Let's say from 81 to 529. When you have 2 lambda by 2 lambda size, okay, you get 625 to 2,304, okay, diversity order. So in this paper, okay, it was reported that the diversity order actually increases so much by introducing position flexibility for antenna, okay? So taking MIMO to MIMO+FAS is really, really a powerful stuff, okay? So another potential application for free antenna system is what I call free antenna multiple access. Remember the comments that I made about the scalability issue for multi-user MIMO, or, you know, multi-user mass MIMO, whatever, that we need channel state information to be available at the transmitter side. So we need to do estimation, you know, high quality, and then we need this CSI to be feedback, okay, soon enough, okay. So we have quality CSI in order to do pre-coding, okay. So that's what we need. Of course, if you do it for NOMA, RSMA, you also need you still need this channel state information at the transmitter side so that you can pick, you can select appropriate users to be in the group to do NOMA or RSMA, and also you need to do power control, yeah. So therefore, you know, the CSI at the base station is needed for both, either it's multi-user MIMO or NOMA or RSMA, okay, there's no exception. Now, but if we use position flexibility empowered by a free antenna system, the possibility is that, okay, we can do this multiple access in a much more simple way, okay? So this is an example. If we have 2 users, 2 base station in the downlink, base station antenna 1 talk to user 1, base station antenna 2 talk to user 2, on the same frequency, same time. Now, the difference here is that the user 1, user 2 is equipped with free antenna system. So we have the position flexibility where we can change the position, okay, of the antenna for reception. So let's focus on user one. What happens is that you actually get two signals. One is the blue signal, the other one is the red signal. Remember, once you have the front end system, you don't have one single signal in space, but you have like a signal spectrum in space, okay, that you can access because of these sort of flexible receiver architecture. So what we see is that channel fading, which is the phenomenon which we hate, okay, because it's a channel impairment that we try to avoid for decades, now becomes a plus, becomes an opportunity, because fading happens no matter what, okay, either for your desired signal or your interference. So therefore, in there, what we see is that the blue signal is what we want, the red signal is what we don't want. But the good news is that the red signal could suffer from fading in some position. These fading happens naturally because of multipath feeding. Then at that position, if you tune in to receive the signal, then you see no interference from the red, but you get your signal from the blue. Then you can avoid interference without doing pre-coding. That means you don't need power control, you don't need pre-coding, you don't need channel state information at the transmitter side, yet you can receive your signal interference-free. Because interference-free, that means that you don't need to do interference cancellation like NOMA or RSMA as well. So therefore, this is so good, okay? So how about user two? User two, you can independently do the same thing, okay? Following the same idea. But in this time, in this user, what you want is just look for the interference now. Okay, so look for the place where the blue signals disappear, and then you go to that place, you get your red signal, bingo. Okay, so this is really nice. Okay, we actually report these results in these two papers. Of course, there is a little bit of different variation of how do we select the position, what is the position that we like to go to in order to avoid interference. So there's what we call the fast version and then the slow version. Without going into the details, what I want to say is that, in fact, this is quite a practical approach to avoid interference. And then we can actually deal with 2 user, 3 user, 4 user, 5 user, 6 user like that, okay? But probably not more than 6 user, because when there are too many users, too many interference, okay, then it would be unlikely that you can find a position where all the interference or the aggregate interference become very weak, okay? So this doesn't actually happen, okay? So therefore, if there are too many users, too many interference, so it doesn't work, okay? But there's the other idea is that actually even 100 users, that's no problem. But these idea still using the free system and to do it, but it's so hard to realize, okay? So therefore, practically, people tend to focus more on the realistic approach, which is only able to deal with several users, like 5 or 6 users, okay? So because of that limitation, so earlier, okay, this year, okay, I published a paper in the IP-wise transaction wireless communication, which was published, it was just published in June. So I sort of changed the idea a little bit. I still want a simple receiver architecture to avoid interference. But I realized that if I have this free antenna system for reception, then if I try to choose one particular position to receive the signal, I would be unlucky all the time, because it's not likely that there would be one position where all the aggregate interference or all the interference would become very weak. So it doesn't actually happen, okay? So therefore, that free antenna multiple access method doesn't work when there are too many interference, okay? So therefore, I make a little bit of tweaks, okay, on that approach. Then I think, like, what if I'm not selecting one position? I'm selecting, let's say, a number position, let's say 10, 20 position to receive the signal. And then I sort of combine the signals. Would that help? Well, in general, yes, but if I select 10 positions to receive a signal and I also need 10 RFKs to do it, then this idea would never be interesting, okay? Because that would be too much, okay? How can we expect a lot of RFKs at the receiver? Okay, no way. That's too expensive, okay? So therefore, I need to keep the receiver architecture at low complexity and realistic, yet I want to increase the interference rejection capability. So in the end, I came up with this idea. I called it compact ultra massive antenna array. It's just a name, but actually it's still free antenna system. It's a small variation of the free antenna multiple axis, in the sense that instead of choosing one position, I choose a lot of position and then to activate that to receive signal, but I don't do any modification when the received signals comes in, and I just aggregate them in the analog domain. Now the question is that you may wonder, okay, if you don't do any co-phasing or signal processing when the signals come in the analog domain, so how are you going to have any gain, okay, on that? If there's no gain, then it's useless, okay, doing architecture like this. Now, the key to this is that, in fact, you don't randomly select a couple of positions, okay, to receive the signal and let them sum up in the analog domain. You carefully select those which they naturally comes in and align in the signal space, okay? Then when you then select those and let them just sum in the analog domain, it would provide you gain, okay? So there are some details that, if you're interested, to go take a look of this paper. So in this sort of standard structure, okay, I actually need a 2 RF chain. In fact, 1 RF chain would work, but 2 RF chain is a natural choice. Then you can do some simple signal processing to do it. Now, the good news is that, okay, before I can only deal with 5, 6 users on the same channel, but now I can push this to 10, 20, even 30 users on the same channels, okay? And that is the ergodic rate, okay, of the network. So you increase the user, it increases the rate, and that is the number of positions, the resolution of the free antenna systems. So remember, this set of capacity or ergodic rates that we achieved it without channel state information at the transmitter side, without performing pre-coding at the transmitter side, without doing power control at the transmitter side, without interference cancellation at the receiver as well. Okay, so therefore, given these background, I think it's pretty impressive if we are able to deal with 30 users on the same channel with only 2 RF chains at each user, okay, and no pre-coding whatsoever. So this is also one area that could be really, really interesting to explore. So, and in fact, with these techniques, or one thing that we try and then we realize is so powerful is that, because, the situation is this, okay, we know there is the idea called multi-user MIMO or massive multi-user MIMO, which is so powerful. Now, let's say, okay, we are contemplating the idea of this free antenna system using this CUMA idea, which we can accommodate like 20, 30 users, okay, on the same channels. It looks very nice as well. But this idea is not going to replace multi-user MIMO, right? Okay, so we need to actually consider the situation where, if they combine, do they help each other, okay, right? Because, a free antenna system, let me try to emphasize here. Free antenna system is not here to replace other technologies, but is here to make other technology greater, better, okay, right? And free antenna system is able to complement existing technology and make everything better, okay? That is the main idea. So therefore, in this world, we actually explore, okay, what happens if we use this CUMA idea at each user, but we keep the multi-user MIMO at the base station for pre-coding. But the good news is that when we do it, okay, instead of requiring instantaneous CSI at the base station for pre-coding, it turns out that we can simply use, okay, statistical CSI at the base station for pre-coding, okay? So then the overhead for channel estimation will be very, very low compared to the instantaneous CSI. You need to maintain every millisecond. You don't need to do that for statistical CSI. So this is the result that we have. That we are able to show that, if we combine extra large MIMO and free antenna system receiver together, we can make extra large MIMO simpler, okay? Because we only need, okay, very simple pre-coding, and we need less CSI because we only require statistical CSI, we are able to support 1,000 or more users because we see that the capacity goes up like linearly like that. And as a comparison, this is the massive MIMO, the conventional massive MIMO. If we don't have instantaneous CSI and we are only relying on statistical CSI, this is what we can get. But if we bring in free antenna system at each user, then using only statistical CSI, we get that result. This result is as good as, if not better, than the massive MIMO with perfect instantaneous CSI for pre-coding. Okay, so therefore, this is quite a lovely opportunity, and then we can actually see the free antenna system. When we have this idea, bring it in, it reduces the requirement for pre-coding, okay, for extra large MIMO, and make extra large MIMO a lot more practical, okay, and then we have this sort of scalability. Here, more than 1,000 bit per second per hertz, okay, this is interesting. So another thing is, like I said, free antenna system is not here to replace other technology, even though I keep saying, yeah, because with the free antenna system, we have the signal spectrum in the spatial domain. We can do multiple axes without pre-coding, without interference cancelling, etc. But in fact, if you love NOMA, you can still do NOMA, okay? But with free antenna system, that free antenna system plays the role of increasing degree of freedom for NOMA to work better. For example, in this paper, we show that, okay, this is, let's say, the NOMA with the existing conventional fixed position antenna, but this is the NOMA with free antenna system. And then we are able to reduce 9 dB energy consumption to achieve the same sum rate, okay? So that is the power of free antenna system, the power of the increased degree of freedom that it can bring to NOMA. Another area which I think a lot of people will love it is ISAC, right? Integrated sensing and communication is an extremely hot topic right now. And in this particular paper, just published in the I3 transition wireless communications. And then we consider an ISAC system in the downlink using multi-sum MIMO. But the interesting thing is that we are introducing free antenna system onto this multi-sum MIMO base station. So therefore, we let the position of the antennas, the base station, to change together with optimizing the beamforming, okay, for sensing communications. Then in our result, what we can see is, let's say the horizontal line are the results where are the capacity results where we are using the fixed multi-sum MIMO beamforming, okay, to do ISAC, okay. So we have a sensing requirement to meet, okay. Given that we meet the requirement, what is the capacity we achieve is what the results that we that are being shown here. So these are the standard fixed position, okay, MIMO base station. But if we allow the position of the antennas to change, like for antenna system, after the optimization, it jumped. You see, the capacity jumped a lot, right? Some like 70%, some 75%, some 84%, like, you know, it's nearly doubling the capacity for ISAC if we introduce this new degree of freedom enabled by free antenna system. So there's, of course, also a possibility of combining RIS technology reconfigured intelligent surfaces and free antenna system together. In this paper, one of these work, we're actually considering the RIS is fixed RIS, but then what if the user have free antenna system, okay, and we have fixed position antenna for the base station, and then we look at how's that, okay, improve the outage probability. So this is one of those results that we get. What we see is this line is the conventional fixed position user, but if we replace this to free antenna system user, you can see the results, you know, is like this. It's like this red and blue line. Like the outage probability slope is deepened, okay, so much, okay? So it actually improved outage probability so much, okay? And of course, like, on the picture on the left, we could also consider free antenna system onto the base station and on the RIS, and then, we can do some kind of optimization. I mean, these will be very, very interesting topic, which I haven't yet explored, but I feel like, creating a pitch, an image like this would be exciting. So this would be one area that would hopefully attract a lot of attention in the near future. So AI and free antenna system everywhere. So like I said, free antenna system is not limited to user. It could be used on base station. It could be used on RIS. It could be used on UAV. It could be used on, vehicles, other sort of mobile devices, or, fixed transmitter receivers. Okay, it doesn't really matter. Because of that, of course, it complicates the channel structures. It makes things complicated. So therefore, it would make optimization so complicated. But we believe that there's going to be a lot of area where we can explore the use of AI, okay, machine learning, technology, okay, techniques that could help establishing some information map, radio spectrum map, whatever, okay, for optimization. So this would be one area in which I also feel there are a lot of promises there. Okay, now, okay, it's close to the end of the presentation now. So before I conclude, I'd like to just quickly go through two experiments, okay, that we recently did, okay, and that shows some measurement data. I think is pretty encouraging in terms of for antenna system. The first experiment was done by Professor Ross Murch from Hong Kong University of Science and Technology. He created this sort of pixel reconfigurable version for free antenna system. Like I said, it's these like 36 sort of puzzles, okay, to make up in a reconfigurable antenna for free antenna system. And from that sort of optimization, he can come up with 12 reconfigurable states. Each state represent an antenna with a different shape, different form, different polarization, and different position. Okay, so basically we have 12 of them. Okay, so we put it in the lab. Okay, we have two conventional transmitters and two receivers. One receiver is this free antenna system receiver. What we want is that we, at the receiver of this free antenna system, excuse me, we measure the signals, okay, from the two transmitters, okay? So we have the transmitter 1 signal and transmitter 2 signal. So these are the measurement data. So the user 1 signal, let's say the blue one, is this. And the user 2 signal is the red one, is this, okay? This is time instance 1, this is time instant 2, this is another time instant. So of course, channel changes when time changes, okay, because of different multipath fading, etc. But what we can see for sure is that this measurement data confirm the possibility or the feasibility of free antenna multiple access. Why? Because then with this antenna, I can, if I'm interested in getting the red signal, I can tune into the first reconfigure state, and then I get, good signal to incidence ratio, okay, to get red signal, because the blue signal is kind of like gone, very, very weak. Or if we want the blue signal, I can turn on to this state and where the blue signal is stronger than the red signal, and then get some decent signal to incidence ratio. Different time instant, I can, do the same thing, right? Like that. So therefore, from these initial experiments with these prototype, we can actually demonstrate that the free antenna multiple access idea is real, okay, and is feasible, okay. We actually also try this for another design, using this method design for antenna system. This work is led by Dr. Liu from Shenzhen Technology University in collaboration with Steve Wong from City University and my colleague Kenneth Tong from UCL. They created these antenna using metamaterials concepts, okay, where they can activate certain point on this surface so that they can relocate the aperture of the antenna, okay, to achieve this position flexibility, okay. So they actually fabricate this. This is the so-called method design for antenna system. Okay, that's the backside with the FPGA, and then we in the lab we consider a free user scenario, free transmitter scenario. They all these free transmitter transmit at the same time, same frequency, so they interfere. So what we look at is that we did let's say 10 independent measurements, so basically 10 independent channel realization. What we see is that we can always change the posture of the antenna to receive the signal where we get a decent signal to interference ratio. Again, confirming the feasibility of free antenna multiple access by using a high resolution position flexible free antenna system. Okay. So that's the experiments, okay, and then we're going to do more. Okay, I hope that in the future I'm going to share more. So this is the conclusion. That concludes my talk. I think the main ideas that I covered today is that for intent. Now, hopefully, now you know what is free intent system. It's a concept. Bruce Lee say, "Be water, my friend." I say, "Be water, my antenna." Okay, to actually introduce this sort of ultimate flexibility. Okay, for antenna, to increase degree of freedom. Okay, and this idea is not specific. Okay, to any implementation approach. You can do movement mechanism if you want to. Okay, if this meets your delay requirement, you can do metamaterial based design like what I shared today, and then you can also do this significant pixel ideas as well. The options are many, okay, and I'm pretty sure that in the near future you see other ideas being tried to realize for antenna system as well. There would be better designs, okay, in the future. So I promise that there will be more experimental results to come to share. Hopefully this year, if not, will be next year, okay. I would love to do that. And I also like to share that, we have created a website for free antenna system for all. Go there, okay. And if you work on this area, you have new materials to share, let us know, and then we'll put it on the website. So the website is not just to advertise our own work, and then we also like to gather all these sort of contribution from around the world, different researchers, to put it on one place to help the community. And in that, we also recently created a WeChat group, okay, for the free antenna system research community. That's the logo, okay, for the WeChat public account. So we have created this WeChat group, okay. So but WeChat, okay, remember this is an app, but this app is not limited to Chinese people, okay. In fact, in the group we also have a lot of other non-Chinese researchers joining the group, because in WeChat, this app, they have these instant translation features. So therefore, you won't feel left out, okay? If somebody, okay, messaging in Chinese, no worry, okay? You can translate it easily inside the app. So that's no problem. There's no restriction. There's a huge interest, okay, for these WeChat groups. So we actually create two groups now. One group already hit the maximum 500 people, because we cannot have more people on that group, because 500 is the limit. So therefore, we have created another one. Another one is actually identical. We'll post same thing on both groups. Even the second group now have more than 190 people, okay? So if you want to join, okay, scan this QR code to join. If you scan this QR code, but it turns out not to be working, because maybe we hit 200 limit, and then after 200, we need individual invitation, do contact me, and then I would privately invite you to join the group, okay? Okay, so Bruce Lee said, if you spend too much time thinking about a thing, you'll never get it done. That is a reminder to me, okay? So in fact, I had this idea of free internet system nearly 10 years now, but the work just started to appear back from 2020 when I feel like taking some risk. And then since then, I couldn't stop. And then hopefully this area is getting some momentum. And then you also find that is interesting, and you can easily bring this to your own research area. Okay, and let's work together to grow in this area. Really, my last slide. I like to advertise this call for papers for JSAC. Okay, so we are organizing this special issue on free internet system and other next generation reconfigurable internet system for wireless communications, with a submission deadline 15th of February. There's still some time now, it's just September. So do try to work on this area, and then I'm looking forward to your submission. Okay. So that's all for this video. I hope you enjoy this video, and then you find this video helpful to you. Okay. Bye-bye now.